rest of the molecule is the same, which leaves us with a serious problem. At the end of the first series, once we split this apart, I said we got down here, we got a phosphate down here. But I said at this point, you can't give this phosphate to ADP to make ATP, or you'll just be back where you started from, and there won't be any point in it. And you'd be out of phosphates. You couldn't go any further. And so that tricky phosphate sneak got the extra phosphate on there so that you could make the ATP to break even and still leave some phosphate, so potentially you can come out ahead. But how are you going to get the other phosphate on there, and where is it going to come from? Or I guess you don't need another phosphate. How are you going to get the energy into that phosphate to transfer it to ADP? Now notice you can't go sneaking it on here. The tricky phosphate sneak, what was at the top of the molecule, was an aldehyde group, and that's mildly reactive. It'll react. Sugars and acids do react. That's a fairly common chemical reaction. And, it goes, it's spontaneous. It doesn't take a lot of effort to do that. And so it's easy to sneak a phosphate onto this position, but now you've turned that position into, boy, oh boy, I got to watch how much I get this mixed up, turned it into an acid. And of course you can't sneak a phosphate on that. That was the whole point. The acid-acid bond up here, double acid, an anhydride, tends to fall apart very rapidly and with a big energy release, a lot of heat release in water. And so it doesn't work. The second time, you can't trick another low-energy phosphate into coming on there. It can't. Okay, it's a big energy barrier. You can't sneak it on there. There's no room to sneak it in there. It looks like a dead end. Now you see why evolution's so slow. Okay, billions of years rolled by. They'd wasted all the energy they invested and got nowhere. And here this molecule is just hanging around, woe is me, what can I do? Okay. And then somebody came up with the trickier phosphate shuffle. Okay. And this is wild. And, I can't believe something like this would happen. So here you've got this phosphate down here in the third position. And chemically speaking, there's just nothing you can do with it. Doesn't have enough energy to add to ADP to make phosphate. You can't even use ATP to add a phosphate up there. And so it looks like a dead end, which means the end of life. You got no energy harvest. You can't use glucose as this energy storage stuff. And so it almost looks like out of desperation. The molecule is thinking and figuring and guessing what's going to happen. Well, I don't know, everything else has failed. Let's just trade places. I can't believe this. Okay, so what happens to this? Here's 3 PGAL, or PGA, the phosphate on the third carbon. And so all that happens here is it changes place with a hydrogen up here, the OH group. And now you've got the phosphate on the second carbon. Okay, well that's kind of wild. Now that's such a rare reaction that the enzyme involved is called a mutase. Although it's an example of an isomerase because it just rearranged the parts. You've got the same number of parts, you just arranged them differently. The phosphate's stuck in the middle instead of on the end. Well, what does that get you? And the answer is absolutely nothing. Okay, you're nowhere. Okay, so that doesn't have any more energy than it did when it was stuck on the end. In fact, you have to rotate this acid up here out of the way because the two of them are getting too close together and the molecule's going to fall apart in water if you don't do something quick. And so that's why evolution's so slow. These all disintegrated before they thought of the next. No, okay. What are you going to do? Okay, and so now you've got this anticipation again. Planning ahead, a goal. This is goal-oriented. This reaction right here has no value in and of itself, could not be promoted by natural selection as a better survivor than the molecule in front of it. In fact, even with the enzyme there, you have to have a little bit of this stuff in the cell all the time, 2,3-di-PGA. And that's got to be, that's like a porcupine metabolically. That thing has got it's got 3 great big reactive groups, all within a short distance, virtually battling each other. Actually, it's like Siamese porcupines, only triplet Siamese porcupines. And they're just bent on, tearing each other to pieces. This stuff can't possibly last very long. If you just drop some in the water, I'm sure the glass of water would heat up as this stuff disintegrated. And so here you got this triple-headed Siamese porcupine working with this enzyme, and all it does is shift the phosphate from the third to the second position and leaves you wondering, why? And what's the answer? Anticipation. You had something in mind. But again, you have to wait. It's like the kid. Well, can I open my Christmas presents now? No, you got to wait till December 25th. Well, one now, one tomorrow. So, evolution can only reward immediate survival value, and there ain't none. And then the next step comes along, and that looks like an act of desperation leading nowhere to. And this is water. When I was a kid, they used to tell me, that scientists believe you can't have life without water. And I thought, boy, I hope I don't grow to be a scientist that has that little imagination. But after I learned what water does, oh, wow. Water is so tied up with the essence of what life is on any level that it's really hard to imagine. It shows up all over the place in metabolism. Well, here, there's a molecule. Again, it's kind of an unusual one. The other molecules are categories that get used over and over again. Well, this is something called an enolase. And what it does is take this hydrogen and that OH group and put them together to make water. Wow. Okay, well, you didn't want to make water. The cell's full of water. You got plenty of water. So that wasn't the goal, was to make water. But when you do that, then you get one of the weirdest molecules in all of metabolism with a perfect name, PEP. Okay, now that stands for phosphoenol pyruvate, but PEP is a really good name for it. This is an incredibly energetic molecule. It's got almost twice the bond energy that ATP